before we go to the 8.2, where we actually will find methods to solve recursive relations, and then so we have seen how to solve these, but kind of by hand, like by just trying to guess a formula. But we will see much better ways of doing that. That's 8.2. And in 8.3, we will apply this to find the complexities of certain recursive algorithms. So 8.3 will talk about different types of recursive algorithms. And I want to talk about those first before we go to 8.2, because it's also actually part of 8.1. I didn't cover all of 8.1, perhaps you noticed this already. So what I want to still do is talk about recursive algorithms. So algorithms that use recurrence or recursive relations. And I'm going to do only really one example here. And there are different types we will see. So let me perhaps say this. There were two types that we will discuss, the divide and conquer algorithms, and those are the ones that we're going to discuss in 8.3. Okay, and then the one that I'm going to discuss today is a dynamic programming or dynamic algorithms that is in 8.1. That's actually, it starts on page 507 if you want to start reading. I'll write down the readings on the readings are posted also on the webpage. I will say a little bit about divide and conquer perhaps at the end, but let's go to the dynamic one. So I'm going to talk about this. And I'm going to do a particular problem, a problem that we actually already handled, I think in section 5.4. We saw an algorithm that figures out if you have a couple of talks, you have one lecture hall, and you have a bunch of talks that have to be scheduled in that lecture hall, and the times of these talks are fixed. And then you have to find like a schedule, an optimal schedule that you can. In 5.4, when we talked about it first time, and that was in Discrete Math 1, we tried to find a schedule that contained as many lectures as possible, or perhaps I forget now what we optimized. So we might have optimized the total amount of lecture time spent. So trying to cover as much lecture as we could with these talks. And we had designed an algorithm but that algorithm was different from what we do today, because we're going to change the constraint, or better our goal. Our goal is our objective is going to be so we have these talks, but moreover these talks have a number of, let's say, people that have subscribed for that talk, right? So a number of attendees. We know exactly how many people will attend a given talk. And so what we want to optimize, if you think about this, one thing that perhaps you want to optimize, because let's say you can ask a little fee for people attending these talks, is to get as much people as possible. So now therefore it could be, of course, that if you have a schedule, let's say, let's put a very simple schedule here. We have at 8, 9, 10, and 11, and you have one talk here, and there's 5 people, and there's one type here that is 10 people, and then there's another talk let's put them 100 people, and here's a talk that 70 people. So of course we could schedule, so we call this talk 1, talk 2, and 3. You see from this example here that these two are compatible, so 1 and 3 can be scheduled together. So in the previous case, that would be more scheduling that we would do, right? And we would cover actually the whole time period, so we would optimally use our room as far as talks is concerned, but not as far as attendees is concerned, because just taking 2, that means that we will have an empty slot for an hour, but we will have more attendees. So it's a different type of question, therefore. Now, this is perhaps a very simple example, so I'm going to go to an example that the book gives. And and so let's look at a concrete example. Say we have, I'm going to go here. I put into kind of a schedule here of the 7 talks. There are 7 talks, and you see when they start and end. Okay, and the exact times is not so important. What matters is there are overlaps or not. Okay, so everything starts at 8 a.m. Sorry, the green went a little bit out of I'm not very good at coloring within the lines, okay? So you have these 7 talks, and we want to schedule them, but these 7 talks, I'm not going to give you the data here, but one of the exercises will be where you really actually know how many people will attend each of these 7 talks, and then you have to find what's the best, what is the optimal number of attendees. That's going to be a homework problem. So in this problem, I'm going to do it, work out the whole thing in general, and then you, in the homework problems, you're going to try to apply it to this specific case. Okay, but we need this. This is not so simple anymore. I mean, there is of course ways that we could do it where we do just try all possible schedules, but that is very bad programming. Okay, and so what we will do is a so-called dynamic programming. Now, what is the difference? So I told you there are 2 types of the recursive algorithms, which means that they reduce the problem to less objects, right? And what is the difference here? This is subdivides in non-overlapping subproblems. So that is the divide part. We divide everything so that it is non-overlapping. So perhaps to give just an example, as I said, I'll come back perhaps on towards the end of this, but we will definitely discuss this more in 8.3, is the binary search. Remember, in binary search, what we would do is you take your total list, cut it in half, and then search, binary search. Right, yes. No, binary search, right. It's an ordered list, sorry. It's an ordered list, it's an ordered list, you cut it in half, and you check in each of those whether your thing is there, right? Simple like thing. So you divide in 2 separate things. That's the divide part, and the conquer part we'll talk about much more of that in 8.3 is where you put it together again. Now dynamic, what's the difference here is exactly in that word overlapping, non-overlapping. So now it's to overlapping subproblems. So you're not dividing it anymore, you're reducing it. So in other words, you're gonna do for less, but that these problems are any of these problems that you reduce it to, 2 of those might have a lot of that in common or not. We don't know yet. We cannot know in advance. So that's the difference. So in other words, let me underline it here that you so highlight it. Non-overlapping is divide and conquer, and this is overlapping that we're going to talk about. Okay. So we have to set this up, and the first thing we're going to define is a new function, the function P of I. So we have how many talks? So N is going to be the number of talks, in this case 7, and I and J will be referred. So okay, let me perhaps put it this way. What else do we have? We have the start times, and of course this is the ending times. So start time, and this is end time. Okay, they always have to be this way. And we have already arranged this so. This is a separate problem, so in the text they do talk about it, but we kind of ignore it and we say let's just assume that we have put them in order of end talks. Like the way that you see it's ordered this way, okay? Not in starting times. Notice that the next one, the first number 1 is the only one starts at 8 a.m., but number 5 starts at 8:30, somewhere around there. But why is it not the second one? Because we're ordering according to last time. So we have A1 is going to be E2 is less than E3, etc. So it's these end times here, these are the end times, right? It has to look like this, okay? We assume that we have list everything like that. So I is going from 1 to 7 here, because we have 7 talks. Of course, in general, is I from 1 to n. And then we have the WI is the number of attendees in each of these talks. of talk I. So I is the way that we enumerate our talks. Okay, so we have to define something. We're going to define P of I. And what is P of I? Is going to be the last talk. I mean our talks are ordered, right? So there's 1, 2, 3. The talk with highest number. I'm just going to say I shouldn't call it perhaps last talk. Yeah, let me go. The latest talk that is compatible with talk I. Now, what does this compatible mean? Well, compatible means exactly that they don't overlap. No overlap. Okay, so let's figure out what the p-value is for each of these talks here, right? So for each talk, we can find a p-value. Now, it could well be that there is no such latest talk. So otherwise, in other words, if there is no latest talk that is compatible, right, then we put pi equal to 0. Latest talk, I forgot one thing. Latest talk compatible with talk E below I. Okay, perhaps best to see this on an example. Let's look somewhere that we have something happening. Let's look at 3 here. Let's look at talk 3. So you see talk 3, what is talk 3 compatible with? It's compatible with 1 because it starts at 10 a.m. when one ends. Okay, so we agree that compatible will mean that exactly one talk ends, the other starts. Of course, technically that's not really possible. People have to come in and out, but we'll say every talk always stops a minute before, and that gives time for people to move in or out. Okay. Or this could be Zoom sessions, right? Because since we're in COVID, semi-lockdown, so let's just say there are Zoom sessions at several hours. So there's no problem to start one Zoom session right after the other one ends. Okay. But we have only one computer, so that's why we have to organize these talks. Okay, so PI, so what is this PI for P3? Let's look at P3. So we said, okay, 1 is compatible, 2 is not compatible. So the largest one, the latest one that is compatible with it is 1. So P3 is 1. So what about P2 then? Let's look at what is the value for 2. Well, there is no talk that is compatible and is below it, right? So it always has to be low. So of course, yeah, 7 is compatible, but we don't take that. It's only talks below I. Okay, so we're looking for a talk below 2 that is compatible. There is none, so this would be 0. And of course, the same here for 1 because there are no talks yet. Okay, let's see, what is it for 4? So try now, stop the video for yourself and try to figure out what these values are. Okay, but I'm going to go on. For 4, well, let's see. Actually, none of the previous talks is compatible with it because it starts too early. So this actually is 0. Okay, so what about 5? Same thing. Nothing is compatible with 5, that before 5, so that's 0. What about 6? 6, okay, 1 is okay, and 2 is okay, 3 not. 4 and 5 no longer. Well, no, I shouldn't say that, right? Yeah, so I have to say the last one, so 2. So this is 2, that's the last one that's compatible with it. And what about 7? Well, 1 is compatible, 2 is compatible, 3 is compatible, 4 is 4 compatible. I might have drawn it a little bit awkwardly, but it should have been compatible. Sorry about that. They're supposed to start and end at 1 p.m. here. So this is, sorry, let me get my drawing a little bit better here of this guy. This is supposed to be starting exactly at 1 p.m. when 4 ends. The exact times are in the textbook. So, okay, so in other words, 4 is still compatible. 3 is also compatible with, but 4 is still compatible, so the p-value here is 4. Okay, so these are the p-values, and well, we have to calculate those. We will put that in our algorithm eventually, but we see how you calculate this, right? So here we already have to look at previous ones to see what the value of this pi is. Now, okay, here is what the algorithm is going to do. So what as I said, it's recursive, so we're going to try So find, no, let's call it this way, Tj is going to be the most attendees in a schedule of talks 1 up to j. So we're going to do the first j many and see what's our best optimal schedule that we can get with the first j many. Okay? So that's what Tj will be. Tj will calculate how much it is, and eventually the algorithm will tell us what we want is T of n, because that will be the most attendees in the schedule of talks 1 up to n, in other words, all talks, right? So Tn is what we want. Okay, so what we do is the following. There are two cases. So case 1, J belongs to an optimal schedule. So yeah, what is an optimal schedule? Is a schedule that has the most popular people, right? It's a solution of our problem, okay? So, okay, suppose that it belongs to an optimal schedule. What does this now mean, right? So this means that, well, let's think about what it tells me about the schedule 1 involving all the way up to pj. Yeah, let's think about those talks. Now remember, we always have that pi is less than I, right? Because here we're looking for talks that are compatible with I, but that are below I. You saw that here from our calculations, right? That this was always less than. Okay, so this is a smaller list than the list that we're looking at. And in fact, what we for sure know is that these guys, pj plus 1, all the way up to j minus 1, cannot belong to an optimal schedule because they conflict, right? Remember, pj was the last one that has no conflict with j. These ones, since j is in an optimal schedule, in other words, j has to be in our schedule, these guys cannot be in our schedule, right? Because they, if you put in j, the ones that I just boxed are in conflict with j, right? An optimal, sorry, I repeat, an optimal schedule means that j is part of our solution. So this is what weird, right? We don't know the solution yet, but we say, what happens if j is part of our solution? Well, we say, if j is part of a solution, in other words, it's part of the final list of talks, then all the other talks, of course, have to be compatible with it. Now, we know that these guys, by definition, this is if you look at the definition here of pi, the ones that are more than pi, these are the latest one that is compatible. So everything below, after it, is no longer compatible. So these are not compatible. So they cannot be part of an optimal schedule. So let me put this in red. So say they are already out. Okay. So this means now, our optimal schedule must contain these talks together with that one. Right? Because we know that j is a part of an optimal schedule. By the way, I don't know, and I'm not saying that all of these are part of an optimal schedule. Optimal schedule is part of these talks. Okay? Because, so this is where a sub-problem. We have to now find the optimal schedule for all these talks, but that not means, that by far doesn't mean all of them, it means some of them. Okay? So what does this now mean for wj? What is for tj, the number. Remember, j is part of our optimal schedule, so wj is going to be part of our maximal number of attendees plus the maximum of the attendees of this part of the optimal schedule, that is t of pj. Right? Remember, t of an index means the number of people in most attendees in an optimal schedule involving the first j talks. Okay, so what happens now if j does not belong to an optimal schedule? Okay, let's think about what happens then. This means that, well, let's look at now these talks, all these talks, one less, okay? The optimal schedule that I can find within this guy is going to be the same as the one if I add j, because j is never going to be part of it. So if I add j to this list, the one that I just boxed, I'm not going to get any better solution because j is not going to be part of an optimal solution. So if the optimal solution must already lie in the boxed guy, that means that t of j is going to be also tj minus 1. The best number of solutions comes from these other talks, not from j itself, because j is not part of an optimal schedule. So that's where we are. So what does this now mean? What does this mean is we're trying to mic as many people as possible, right? So the problem is we don't have one formula for tj, the value of t. The value of t is either this or that, but which one is it? Well, the one that is highest, right? Because we try to make it as high as possible. So our conclusion is, conclusion, Tj is going to be, whichever of the two is the biggest. So the maximum of Tj minus 1 or Wj plus Tp of j. Okay? Although, you see, what is happening? When we divided in case 1 and in case 2, we pretended that we knew whether j was in an optimal schedule or not. But in fact, we don't know. That's the whole point. We're trying to find that out. So if we don't know in which of these two cases are, the only thing we can say, well, is the best value comes from either case, which gives me the best solution, right? These are two possibilities. Which of these two gives me the best? That's going to be the best. Right? So it's either this or that. Okay? So that's, and now we can easily write down an algorithm. Now, this is a very typical also for recursive algorithms. Recursive algorithms, we have discussed this already a bit, we saw this for instance when you have to calculate a Fibonacci sequence, right? If you do this recursively, you have to go back and back and back and back, but each time you go, you have to do a lot of calculations if you do not store the values of your calculations on the way. If you keep just repeating the process without storing the values. So that is, if you do like naive recursive programming, then you don't store anything, and that means you're going to have to do a lot of calculations. So this is the technique is called memoization. It's a technique of algorithms which we don't really, we are not so much into the business of designing algorithms optimally. We are just discussing them. So here is the crux of the procedure. So let's write down the algorithm. So remember, how did I do this, right? So big one. So procedure. They call it maximum attendees. So I'm gonna just make it. I call it max attendees. Okay, and I'm not going to write down the details. Look at there. I have already said here what the data are. Of course, n is now in general the number of talks, right? And in the example it was 7, but in general this is the data. So the data is already assumed to be in the format that I discussed here. Okay. So max attendancy, and then what do you do? Well, first of all, we have to calculate these PJs because they do play a role here, right? You see in the formula they do appear here. So we need to write down that, but that's very easy with a for loop. So for, and remember we are trying to calculate them for each of the talks, right? From talk 1 up to 2n. So our loop will go from 1 to n. Okay. So j going from 1 to n. So what are the possibilities? Well, if let's say, yeah, if no talk I less than this particular j. We're trying to calculate pj, so our counter j is setting up to calculate pj. So that what follows now is a calculation of pj. If no talk I less than j is compatible with talk j, well, then we have said, remember, there was this case where we had zeros values, right? If there's nothing, we say it's 0. Okay, so then pj, we put it equal to 0. Else, sorry, I should have put it underneath there, but okay. Else, if there is one, then well, take the one that is the biggest one. Else, pj, sorry, I should have written underneath, but it's easier. It's the maximum I less than j if I is compatible with j. Now you say, okay, what is this being compatible? Can we check this? Yeah, of course. What does it mean to be compatible? Compatible means that, so I is compatible with j. What does that mean? That the end time of the I is less than the starting time or equal to the starting time of j. That is just basically checking this condition. It's just nicer to write compatible than write down this condition. Okay, but it is really just this compatible is just saying this inequality here. So that's all very well, nicely programmable. Okay, so now this is our setup for P. Now we're going to start with T. Well, okay, of course we start with talk 0, nothing has happened, and now we will run from 1 to n to calculate the values of T. Okay, so that is in this one. So for j going from 1 to n, so that's the same thing as before here. J going from 1 to n, I should have copied that instead of yeah. And then what is the value of t? Well, that's given here. We have a recursive value here. It's t of j is the max. I mean, of course, the max, it's easy to find what the max is, right? Of tj minus 1 and wj plus tpj. Now, because we know what pj is, that's the whole point. We have stored that into our we have calculated that. And then, so what is now the optimal value? Well, the optimal value is, of course, attained when n is 1. Sorry, not when n is 1. It's t of n, return t of n. That's going to be the most number of attendees you can have with these n talks. Okay, so that's an example of dynamic programming where we reduce, you see what we reduce to, right? So just repeating here, it's either we reduce it to this case or we reduce it to this case and then add this other talk to it. I'm saying this because in one of the homework problems you're gonna see what is this algorithm give us? It gives us the optimum number, but it doesn't give us what is the optimal schedule, which of course is what you really would want to know, right? It's not just how many, but how to do it. And it's a small modification of this algorithm, that's a homework problem, will tell you how to do that. Okay, so I'm going to leave that for a homework problem, and probably will do it as a solution in homework videos. Okay, and so it means you either go to a case where you have one less, or a case where you have actually far more less in general, pj. Remember, pj could very often be 0, right? This is very often 0. That's why we need to know what t of 0 is. That's crucial that we know this, and of course it is supposed to be 0 because when it's 0 means there's nothing compatible. Okay. Okay. All right. So that's all I want to say about this part. And so very quickly about divide and conquer. I want to give just one example of divide and conquer a little bit more in detail. It's an algorithm that we discussed. Recently in 5.4, it's the merge sort. So just quickly the merge sort, and rather than going to the algorithm, let me just remind you what we did. We have a list of say n, so n elements, but I'm going to take n equal to 8. So I'm going to just take letters, say D, A, X, B, C, F, Y. No, let me put a Y before the F. Y, F, O. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. So what was the merge sort? How does it work? Well, each time we would split in two. Okay. And we would then repeat the algorithm on these smaller ones. Okay. So we would have this guy, and then we would have to split that one in two. So we have DA and XB. Okay. And we would split these two in two. We would have CY and we would have FO. That were the two new lists that we make. Sorry, I put the biggest list on top. And then again we would split in two. So we would have D and A. And then here we would have X and B. Here we would have C and Y. And here we would F and O. So this is so what we break down the list. And what we do then is rebuild it up. So what does that mean? Well, we look at this part. We have these two elements here, and now we're going to merge them so that they are in the correct order. So these two become AD, and these two will become BX, and these two will become CY, and these two will become FO. Okay, that's simple, but the next step is the one where we do something. Now we're going to merge these two. Okay, and we discussed how we merged. There's a different algorithm, and how did the algorithm work? Well, you start with both lists and you look at the first element. So this or this, which is the smallest A. And so you scratch that out and you repeat now. Now the first element is D and the first element is still B. What is the smallest? Well, B. So scratch that out. So now this is the first element. What's the smallest? D. Okay, so that's scratched out and then X remains. Okay, and we do the same here. So what I'm saying here is what the part that I just did is a different algorithm. It's not recursive, right? It's just way it works with two lists. What I was describing is a recursive algorithm. It keeps dividing your list in two until your lists are sorted because they're just one element lists, right? Okay, so now here again we have to merge these two. So we look at the first elements, that is C. Okay, we can scratch that out. So this is now the first element, that's F. We can scratch that out. The first element, that is O. We can scratch that out, and then it's Y left. Okay. Okay, and now we merge these together. So if you want up to here, up to this stage, let me do it. Up to this part here, we were dividing it. Okay, remember the name of this type of algorithm was divide and conquer. Here we were dividing it, and once we had divided it, it was kind of sorted. Now we were conquering it. In other words, putting it back together. Okay, and so finally to merge these two, remember we take the first two, compare. We see that it's A, so A goes away. Now B, okay, B is the least one, so that goes also away. Between C and D, C is the least one, so that goes away. And here comes F, D and F. D is the last one, so that's go away. So we have now, no, F is still the smallest one. A bit to X is now the smallest one here, and F is the smallest one there. That's clearly the smallest F, so F is gone. Now X and O, well, O is the smallest, so O is gone. And then X and Y, Y is now the one left, X and Y. Okay, so that is how the merge sort work. And you see there is no overlap. That's the one thing that I wanted to show you. We have, in all these lists, nowhere have we used, worked with lists of these elements, sublists that have the same elements, right? At each level, all these lists were disjoint. Okay, that's the difference. I just want to point that out, and this is something that we can study in 8.3.